put this. Oh, come on. Put this here. We can kind of see both. So I've got this so-called Newton's cradle, which I don't know. I haven't really checked in the last while, but for a while, when I first looked into the name of this thing, I'd seen a lot of these. They, believe it or not, they call these things Newton's balls as well, but I call it Newton's cradle for obvious reasons. So I'll just do a few little Newton's cradle tricks you've probably seen before. It's kind of fun, mesmerizing just to watch. So if I grab two of these and pull them over. Oh, wait a second. Oh, you can see. You just can't see my screen. Let me present. Fallen into the I didn't present trap again. So now you'll be able to see what you can see, and then you'll also see my screen, which I don't know if this is really any better for you, but when I switch into other stuff, we'll at least be on the same page. So here we go with two pulled out. You get that. And I can keep doing this. If I pull three over here and let go, what do you think is going to kick out on the other side? Three. And if I pull four over here and leave that one still, this is kind of odd, really. It's hard to get it still. Then four pop out the other side, which you would think that pulling four out and letting go is a lot like pulling one out and leaving the four there, but you get a different effect. And then my 9-year-old was playing with this last night. He really wanted me to share this one with you. So if I separate these, I pull these out and then let go, what do you think is going to happen? Oh, it doesn't really go for very long, but it basically for a period of time we'll see the one second from the other end separated from its companions. All right, so the question that I've got for you is why is it that if I pull one out and let it go in, we get one on the other side? Because if you're thinking of conservation of momentum, which this is kind of a conservation of momentum thing, if this one ball has a certain velocity here, then its momentum is its mass times its velocity. And when that one comes out the other side, it's got the same mass times velocity. So the momentum of this ball is transferring to that ball, ultimately. I mean, it goes through these other balls. I don't even want to think about what's happening with the other balls in between. But it's transferring its momentum. But there are other ways it could transfer its momentum. So this one could come down here and hit, and then instead of one coming out, we could have two pop out on the other side. It seems reasonable to me that you could take the momentum from this one and transfer it to two of these, and if you did, how fast would they be going? Anyone want to answer? Let's say the velocity of this is v when it hits this ball. How fast would these two pop out?
1/2 v.
1/2 v, yeah. Or, it might be most reasonable to think that if I hit this, all four of those are going to get moving, and then they'll just move out with a velocity of 1/4 v. Or maybe it'll hit, and then everything will stick together and move with the velocity of 1/5 v. In all those cases, you would have momentum conserved. But only one specific case really happens. If one collides with the other ones, then one pops out. If two collide with the other ones, then two pop out the other side. So, does anybody have any ideas, any insights into why that might be? Or has anybody ever tried to make one of these or thought about making one of these? Do you think you could use just any kind of Any kind of ball for this? Does it have to be... sorry, it's out of the picture now. Does it have to be little steel balls? Could it be rubber balls? Could it be foam balls? Has anybody ever seen one of these with rubber balls? I haven't. Nor foam ball. It's always steel balls. In a few, I think I might have seen some glass balls. So there's something about the collision between steel balls and glass balls, gas molecules, which are way too small to manipulate and actually do this with. Does anybody know what's special about this collision, other than the fact that momentum is being conserved? And, well, the answer is they're very efficient at transferring energy as well. So in this collision, it's pretty close to conserving mechanical energy. So the kinetic energy that this has when it hits here is pretty close, almost exactly equal to the kinetic energy that this has. And one way you can tell that energy is conserved is because this goes on for a long, long time. Somebody asked how long will it go yesterday, and I started timing, and it went long enough that I forgot I was timing by the end of it. I don't know. It was 14 minutes later, my daughter came into the classroom and basically asked the same question. I said, oh, yeah, well, I don't know. I tried to time these, but just forgot I was timing them. So the energy stays in these for a long time. And it just so happens that the only way for me to release this one and it to hit and it to do two things, conserve momentum and also conserve kinetic energy, is for one ball to pop out. If mass times velocity of this has to equal mass times velocity of whatever comes out, and 1/2 mv squared for this has to equal 1/2 mv squared for whatever comes out, the only way for this to happen is one to go in and one to come out. You could prove that mathematically, but let's not do that. That would take a while. Same thing with two. The only way to conserve both momentum and kinetic energy is if two come out. So if you did this with foam balls or rubber balls, it wouldn't work because energy is not conserved, or kinetic energy isn't conserved. When this hit, whatever comes out over here is not going to have the same amount of kinetic energy, and therefore you don't necessarily have to have one ball come out to do that. I suppose if you had just the right kind of efficiency, or what we're going to talk about today called coefficient of restitution, you could create a cooked up version of this where if you have one hit, two come out, or if you have one hit, three come out. I've never taken the time to figure that out, but that might be kind of a cool object to make. All right, so that's the warm-up. The homework. Discuss the homework. Let me switch cameras here and then give people a chance to ask about that. I think the hardest one, really, conceptually, was the boat problem. And then after that, the number 12 and number 13 were just kind of weird. I don't think they were difficult. They were just weird. So you were supposed to do 7, 8, 9, and 10, 11, and 12. Not 13 yet. Does anybody have questions about any of those?
Can you do 12?
Yeah. And I think the main thing is the picture. So if I draw a picture, I'm going to draw a picture for 11 and a picture for 12, because they're basically the same thing. And I want to show how they're similar, and then talk about 12. And like I said, there's nothing really hard going on here. It's just kind of weird. And I didn't create these problems. At some point in the future, I might have to change them, because I'm not sure what the point of a weird problem is. Maybe it's good. Just showing you the different ways you can apply this. So in number 11, we've got this train car, which I'm just going to draw looking like this, like some kind of shopping cart or mining cart. And it's moving along to the right. And there's this load that I'm just going to draw like this that's just suspended here, suppose. And this has a velocity of 0. And this car has a velocity of 8.6 meters per second. And so it's going to move along, and at some point you can just imagine the string breaks. This is going to fall straight down and it's going to land in the cart. And then it's going to stay in the cart, and the cart's going to keep moving along with it. So this is the after picture. If it had some string, it would look like that. So this has got all the momentum in the beginning. This has really no momentum in the x dimension. That's really important. Both of these problems take place in the x dimension. So momentum is mass times velocity, and remember, velocity has direction. So this is a vector quantity, and we could talk about momentum in the y dimension or the x dimension. I haven't really gotten into that, but this problem implies you don't have to worry about the fact that this starts to fall and gains momentum in the y dimension, because that's not going to affect the speed at which it's moving in the x dimension. They're independent. So in the beginning, all the momentum is here, so you could calculate this momentum, just mass times velocity. In the end, all the momentum is here. It's the same momentum that you had there, except now there's a bigger mass. So you just have to add on the mass of this plus the mass of the cart, and those multiplied by the velocity with which they move together equals the momentum from before. So the snow one is really no different. You could just imagine that the snow is one big brick of snow. The only difference really is that the snow trickles in little by little over the course of 90 minutes. So again, like I said, you could say, how much snow are we going to get over the whole 90 minutes? And you could just say, let's imagine it's one big block and it falls in all at once. And that's one way to solve the problem. And to do that, you've got the rate at which the snow is falling in, 3.5 kilograms per minute. So every minute, it's 3.5 kilograms. And 90 minutes is how long the snow is lasting. So you multiply 90 minutes times 3.5 kilograms for every minute, and that gives you the total number of kilograms of snow. And that's what's showing up here in the solution. So my picture would maybe look like this. Here's all the snow falling ahead of the cart that hasn't fallen in it yet. Just like this is the mass that hasn't fallen in the cart yet. The cart's got all the momentum. But then 90 minutes later, what you're going to see is that the cart is moving along, and it's got, 90 times 3.5 kilograms of snow added to it now. This snow, since it's falling vertically, doesn't have any momentum, so it's just extra mass added on here. So what you would do to solve this, I'm going to do it a different way. I'm just going to write out the law of conservation of momentum. It would be the mass of the cart times the velocity of the cart, initial, plus the mass of the snow times the velocity of the snow, initial, and this is 0. So we're assuming that it's in the x dimension, so its x velocity is 0. And then in the end, everything is kind of together, so I could do the mass of the cart plus the snow times v equals the total momentum. So in the beginning, the cart is 3,800 kilograms and its speed is 8.6, so this is 3,800 times 8.6 meters per second. And the snow has no, in the y dimension it's got momentum, but in the x dimension it has 0 momentum. And then in the end, the mass of the cart plus the snow is going to be 3,800 kilograms plus 90 minutes times 3.5 kilograms per minute. That's the total mass of the cart then, times whatever v is. So multiply that, divide it by all this, and then you'll have v. Does that do it? I can't remember who it was. That Sam?
Yeah, thank you.
Okay. Oh, Gil. That was Gil. All right. Any other questions? That takes care of the weirdness of these two. They're strange. Anybody have any questions about 10? 10 was the only other one I got questions about yesterday. 10's a lot like this. It's just, I guess 10 would be like, this is the child, and this is the boat, and this is the package, except, I guess, in this example, the package would be almost as massive as the boat. But then the child standing in the boat throws the package out to the right, and to conserve momentum, the boat and the child have to have just as much momentum to the left as the package has to the right. So that's how you set that up. Last chance before we move on. Okay, so turn in your packet to elastic and inelastic collisions. These are kind of unfortunate terms, I think. When I hear elastic collision and inelastic collision, I think of elastic. Elastic's kind of this stretchy substance, and I think of rubber balls and all kinds of things that stretch and bounce. But I don't think of steel balls, and I don't think of glass balls, which are probably the best examples of elastic collisions. So let's see, I'm just cheating and making sure that my notes this year kind of stick with my notes last year. So how are they defined? An elastic, the big difference between them is that elastic and inelastic, this conserves kinetic energy and this does not. So elastic, there are a lot of different kinds of inelastic collisions. You can have partly inelastic collisions, or what we sometimes call totally inelastic collisions, and something can be inelastic to different extents. So you can lose more and more and more kinetic energy depending on the kind of collision. But if it's elastic, there's only one possibility. You have exactly as much kinetic energy as you started with. So this is total kinetic energy remains constant, or you could say is conserved. And that's not necessarily the same thing as saying energy is conserved. We're just focusing on kinetic energy here. And we're not going to have collisions that are happening on the slope of a hill. You won't even have to worry about how potential energy might come into effect. Inelastic means that kinetic energy is lost. There won't be any collisions where kinetic energy is gained. You won't come out with more kinetic energy than we had before. And when you have an inelastic collision, this is not perfectly elastic, because I don't know if you can, my microphone's not in my camera, but you can hear that click. So some of this energy that this ball has when it hits there is being converted to sound energy. So we actually are losing a little bit, but we're losing so little that the Newton's cradle still does its thing, more or less. So where does the lost energy go? It goes to heat, sound. In some cases, you might even get light. There's a physics demonstration where you hit two balls together with a piece of paper in between, and you can make burn marks on the balls, or on the paper, from the heat. And you can actually see it in the dark. Potential energy. So you could actually get energy stored in two things. If you have a collision between a couple of springs, or let's say a Nerf dart shoots into a Nerf gun, it could actually possibly cock the spring inside the Nerf gun. I don't know if Nerf guns would work that way, but you could imagine something colliding and compressing a spring and actually storing energy. But you would lose kinetic. And some examples of nearly elastic collisions. So one is a Newton's cradle. Another really common example is billiard balls. So if you play pool, the way the balls collide with one another is pretty much an elastic collision. But again, it's not the kind of thing, you don't think of your billiard balls as being elastic. They seem really hard and unforgiving, but by this definition, the total kinetic energy remains constant, they're elastic. And then another really good example is gas molecules, which we can't really get our hands on to the extent that we can say, hey, watch this gas molecule bounce into another gas molecule. We have to use PhET simulations and things like that for those. All right, so that's it for elastic versus inelastic. But the hard part's about to come up. And the hard part is actually allowing us to avoid the really ugly, mathematically difficult part. So I'm just going to read what I wrote up here at the top. Let's see. When collisions are perfectly elastic, like perfect steel balls, perfect glass balls, both momentum and kinetic energy are conserved. So one can use a system of two equations to find two unknowns when the two objects collide. For example, when the objects with known masses and initial velocities collide, we can find both final velocities. And we can do that because we can set the kinetic energies before and after equal to one another, and we can set the momentums before and after equal to one another, and then we can solve. One equation comes from conservation of momentum, the other from conservation of kinetic energy. However, the math can get ugly. So if you want to try this, you just go right ahead. Have yourself some fun, ugly math time. The alternative is to solve problems using the coefficient of restitution. And here's what it is. It's kind of like, but not exactly, it's kind of like a measure of efficiency. So if I drop a ball and the ball hits the ground and then bounces back up to here, its coefficient of restitution is less than 1, and that means kinetic energy is being lost with every collision with the ground. If I have a ball that I drop from here and it hits the ground and it bounces up just as high as it did before, this is impossible, but if I had this, then the coefficient of restitution would be 1, and this would be perfectly elastic. It would also be 100% efficient. But the coefficient of restitution is not efficiency. So if this bounces 3/4 as high, then the coefficient of restitution is not 0.75. Or if this bounces half as high, the coefficient of restitution is not 0.5. The height of the bounce would give us efficiency, because if it bounces half as high, up here it's got a certain amount of potential energy, and then after the bounce it's got half that much potential energy, so that would be 50% efficient. But coefficient of restitution is based on speeds. So what it says is if this hits the ground going 1 meter per second, and then it leaves the ground going 0.5 meter per second, the coefficient of restitution is 1/2. It's the separation speed over the closing speed. So in this case, we've got one object, which is the Earth, and one object, which is the ball. And the closing speed is the speed with which they move together. And then the separation speed is the speed with which they move apart. And since the Earth doesn't do much moving, in this case we could really think of this as the speed of the ball right before it hits. That's the closing speed, and then the separation speed would be the speed of the ball right after it bounces away. And if the ratio is 1/2, that ball's not going to bounce half as high. That's a different kind of thing. All right, this E is the symbol, which I didn't really come out and say, which is kind of unfortunate because E means other things. But E is the coefficient of restitution. And when E is 1, objects separate as fast as they came together. So this is pretty much an E of 1, or at least approximately 1, close enough to 1. It's perfectly elastic, no kinetic energy is lost. An example is a perfectly bouncy ball that approaches the ground at 2 meters per second and then bounces back up at 2 meters per second. So this ball over here. When E is 0, it doesn't mean that all momentum is lost. It basically means things stick together. So objects don't separate. There is no separation speed. So if you have a collision where a ball shoots a tree, here's a tree over here, and it embeds in the tree, just sticks in there, they don't separate, that would be called perfectly inelastic. You lose kinetic energy because of friction and maybe some other stuff. And I guess my example is a bullet approaching a ballistic pendulum at 500 meters per second. The bullet embeds in the pendulum and they swing up together. Normally we would have done ballistic pendulums by the time we get to this, but we're going to do ballistic pendulums tomorrow. All right. When 1 is greater than E and E is greater than 0, meaning E is between 0 and 1, the objects separate from one another, but not as fast as they came together. So some kinetic energy is lost to friction. Now for the formula, this is a nifty formula, and you can ponder it sometime when you want to. But I kind of, every once in a while, I stop to think about it, and I think, I want to really wrap my mind around that again. Feel free, but I'm not going to derive it. This is the separation speed. So if you have the initial, so here's object A, and it's moving like this toward object B. We could have them both moving. And it's got an initial velocity of VA, and this has an initial velocity of VB. Then, and let's say these two things collide, and then after the collision, A is now flying back to the left, and B is flying back to the right, and this has a new velocity of VA prime, and this has a velocity of VB prime. So why am I dispensing with the whole initial and final thing? I don't know. It's just kind of customary with this formula. Maybe initial and final, just you've got too many subscripts, and having this prime up here just makes things easier to keep track of. So VB minus VA prime would be this velocity, which is positive in my picture, minus this velocity, which is positive in my picture. Make sure you put in the right signs. So you would be subtracting, in this case, a negative number when you're calculating this. So that would give you the separation speed. And then for the closing speed, when they're coming together here, that we switch directions. Instead of doing B minus A, now it's the initial velocity of A minus the initial velocity of B. And this does give you, in the end, the separation speed over closing speed. Notice this doesn't say velocity. This is just how fast they're coming apart divided by how fast they went together. All right. And then an important note, when E is 1, so if coefficient of restitution equals this, when coefficient of restitution is 1, then the separation speed equals the closing speed, and we can write it like that, which we're about to do. So let's do, here's an example problem to work through. I'm going to draw a picture first, or maybe I won't, because I feel like I need all this space, because we've got to do a system of equations. Running out of space. Speaking of space, let me hide myself down here. Maybe I can just get rid of myself. Really not that important. All right, so cart A has a mass of 4 kilograms and an initial velocity of negative 2 meters per second. Cart B has a mass of 3 kilograms and an initial velocity of 0 meters per second. If they collide with perfect elasticity, meaning E equals 1, what are their velocities after the collision? So these two carts, these could be, instead of carts, these could be steel balls. And, you know, I've got the mass of this one, and I've got the mass of that one, and I know their two velocities, and what we're calculating is their velocities after the collision. This would be really hard to do if, I think, if you set it up as, if you tried to use kinetic energy here and not coefficient of restitution. So the first thing I'm going to do is I'm going to use conservation of momentum. Conservation of P. That's to get my first equation. So for equation number 1. So I'll set this up as a conservation of momentum problem or equation. Cart A first has a momentum of 4 kilograms times a velocity of -2. And cart B has a mass of 3 kilograms times a velocity of 0. That makes things kind of easy. And after the collision, cart A still has a mass of 4 kilograms, but it has a velocity of VA prime. So the primes are the final velocities. And the other cart B, still has a mass of 3 kilograms, but it's got a velocity of VB prime. By the way, if you look in my notes where I did this last year, I think I got some of the variables written down wrong. So this is 8 kilograms, or -8 kilograms meters per second, plus 0 equals 4 kilograms times VA prime plus 3 kilograms times VB prime. And I can't remember really what the smart thing to do is, whether I should solve for one of these in terms of one of the others. I think I'm just going to leave this alone for a second, but I'll leave myself a little space. And now I'm going to go to the coefficient of restitution formula. So coefficient of restitution to get my other equation. And since in this case the coefficient of restitution is 1, we know that this fraction is 1, so the numerator and the denominator are equal. So I'm just going to write it this way. So I have VB prime minus VA prime. I don't know either one of those, so I just have to write those as their variables. VB prime minus VA prime equals VA minus VB. So VA is the velocity of cart A, -2, minus, and then VB is the velocity of cart B, which is 0. So this one's a lot easier, simpler than that formula. So I kind of feel like, it might have been a good idea to do this one first. And this is ringing some bells in my mind that maybe this is the first formula I'll start with in the future. Doesn't really matter which one we do. So this is 0. So, oh sorry, this is -2. And I left out my units, meters per second. So if VB prime minus VA prime equals -2 meters per second, I can solve for either of these and then substitute in up there. For the heck of it, I'll just do VB. So I'm going to add VA prime to both sides. And I get VB prime equals I'll call it VA prime minus 2 meters per second. So now I've got VB in terms of VA. I can put that in right there. So I'm glad I left a little space, although it still might get kind of messy. -8 kilograms. By the way, if anybody notices me make any terrible blunders, you just let me know, because sometimes I do. I know the theory, but sometimes I screw up when I'm trying to demonstrate this. So that's the total momentum before. And then after, we've got 4 kilograms times VA prime plus 3 kilograms times VB. And VB is VA prime minus 2 meters per second. I think I'll just keep going and I'll fix this up. I'm going to skip a couple of steps. Or, no, I'm not. But I am going to just take this part, and since I don't have another line below it, I'm going to write what this is equal to right here. So this would be 4 kilograms VA prime, and this would be plus 3 kilograms VA prime minus 6 kilograms meters per second. All right. Making myself some more space to keep working. So on the left side of my equation still I have the momentum before. This is the momentum after. This is also the momentum after. So if I just say this is equal to this, it looks like I can combine like terms. I guess I'm going to add 6 kilograms meters per second to both sides. So over here, if I have negative 8 plus 6, I get negative 2. And on this right side here, I have 4 kilograms VA prime plus 3 kilograms VA prime. So I have 7 kilograms VA prime. So divide both sides by 7, and that means VA prime equals negative 2/7 meters per second. Let me do that on my calculator, see what that is. So negative 0.286. Orion, will you close that door? And now I can go back and find VB. So assuming this is all correct, then VB prime equals negative 2/7 or negative 0.286 meters per second minus 2 meters per second, which would be negative 2.286 meters per second. Voila! Now that's it's a lot of trouble, and you've got to be really careful. I'm going to see if I got the same answer I got last year. I hope I did. Yes, I did. All right, it's a lot of trouble, and you have to be really careful. But it's a whole lot easier than trying to write an equation for conserved momentum, and then another one where instead of this, we would be writing 1/2 mv squared for the first object plus 1/2 mv squared for the second equals 1/2 mv squared final plus 1/2. That just gets to be a terrible mess. This is a mess. That's a terrible mess. So, your assignment is to continue on. Now you have the capability of doing a bit more. And I think I've assigned number 13 through 15. Yeah. So, 13, you can use a lot of the same concepts that we've been going over, conservation of momentum and some other things in number 13 until you get down to F, where you're going to need to look up the coefficient of restitution formula, and then that'll allow you to answer G. So basically, if you don't find that the coefficient of restitution for this collision is 1, then the answer is it's inelastic. And if it is 1, then it is elastic. 14 and 15, you're going to need to do basically what I just went through in order to find the answers. 14 asks you for the velocity of one ball and the mass of another. Now in the example that I just did, we were looking for both the velocities after the collision So like I said earlier, you're going to have two equations, so you can solve for two unknowns. It might be the velocity of one cart and the velocity of the other, or it might be, like in this example, the velocity of one and the mass of the other. And then in this last problem, you're looking for velocities after the collision. That's it. I know I'm supposed to keep you here until 10:45, but that's ridiculous. So you can go